Hi, today we're going over section 9.3, which is reciprocal and quotient identities. So just a reminder that trigonometric identity is a statement for which our trigonometric ratios. Now, the first three ratios we're going to look at are reciprocal identities. So we have our cosecant, which is 1 over sine. With this, we have a restriction that sine of our angle cannot equal 0, so we're not dividing by 0. We have secant theta, which is 1 over cosine theta. So with that, we've got cos cannot equal 0. And then we have cotangent theta, which is 1 over tan theta. And that we also have tan cannot equal 0. We also have our quotient identities. With it, we have tangent of our angle is equal to sine over cosine, with cos of our angle being unable to equal 0. And we have cotangent, which is cosine over sine, where sine cannot equal 0. Okay, so we'll talk about verifying and proving identities. To verify an identity, all we're doing is substituting a value that we're given in for our angle in our equation and seeing if what we have on one side of our equation is what we get on the other side of the equation. If it is, we can say our equation is verified, which just shows that it has the same value at that particular angle. Now, to see if the identities are the exact same, we do trig proofs. So to prove an identity, we use proven trigonometric identities to show that each side of the equation can be written the same. Okay, so for example, we'll have a few questions where we're verifying our identity for an angle 30 degrees, and then we're going to prove identity, so show that they are actually the same on both sides. So this first one, we have secant theta times 1 plus cos theta equals 1 plus secant theta. So for part I, it's verifying our identity, so we'd have secant of 30 degrees times 1 plus cos of 30 degrees equals 1 plus secant of 30 degrees. So we'll put this in the calculator and see what we get for each side. So on this side, we get 2.1547. This side, we also get 2.1547. So we have verified these because these are the same. Now we'll prove that they are actually the same thing by doing a trig proof. So start out by writing what we have here. So we've got secant theta times 1 plus cos theta equals 1 plus secant theta. Now with trig proofs, what we're trying to do is make it so we have the exact same thing on both sides of our equation. Now with proofs, we don't move stuff from side to side. So whatever's on this side stays on this side. We don't move anything from this side to this side, and vice versa. Nothing from here will move to here. Now, typically with trig proofs, we'll only work on one side of the equation at once, and we'll try to simplify it as much as possible. So I usually choose whatever side looks more complex and start with that side. So this one has more terms, so therefore more complex. So I would start by working on this side. So secant, we know, is 1 over cos. So I can replace this with 1 over cos theta. And then that's being multiplied by 1 plus cos theta. And that's equal to 1 plus secant theta. Now, if I multiply this in, 1 over cos theta times 1 is 1 over cos theta. 1 over cos theta times cos theta would be 1. And then cos theta is secant theta. So we've got secant theta plus 1 equals secant theta, or sorry, 1 plus secant theta. Now, these, even though they are written slightly different, are the exact same. So therefore, we can say that we have proven this identity. So we can say identity proven. For our next one, we have 1 minus tan theta equals cotangent theta minus 1 over cotangent theta. So we'll do the same thing. We're first going to verify for 30 degrees. So we're just going to substitute 30 degrees in for each angle. So you've got 1 minus tan of 30 equals cotangent of 30 minus 1 over cotangent of 30. Plug these in a calculator, and for this side, we get 0.4226. Doing the same thing on the other side, we get the same value, so we have verified it. So now we'll try to prove that those identities are the same. So we've got 1 minus tan theta equals cotangent theta minus 1 over cotangent theta. So in this case, I will probably start working on this side because this one looks more complex, and I'll go and try to simplify it so it matches what's on this side. Now, with cotangent, earlier on, we went over two different identities that can have. So we have the one that is 1 over tan, and we also have the one that's cos over sine. Now, in this case, because this side has tan, I'm probably going to use the one that's 1 over tan. If on this side I didn't have tan, but I had sine or cos, then I would be using the one that uses the cos and the sine. So I have 1 minus tan theta equals, cotangent is 1 over tan theta minus 1 over 1 over tan theta. What I'm probably going to want to do to simplify this is, because I have these extra fractions, I might just multiply the numerator and denominator by tan theta, which I'm able to do because if I'm multiplying by tan theta over tan theta, that's the same as multiplying by 1. So that gives us 1 minus tan theta is equal to 1 over tan theta times tan theta would be 1. Negative 1 times tan theta is negative tan theta. And then 1 over tan theta times tan theta would be 1. So it simplifies to 1 minus tan theta equals 1 minus tan theta. So we got both sides to be the exact same. So we can say our identity is verified or proven. Okay, so with these, we also will sometimes have to state restrictions if required, if the situations arise. So for example, for each identity, determine the non-permissible values of our angle and then prove the identity. Okay, so this one, cotangent, is the same as cos over sine, so therefore sine theta cannot equal 0. And this one would be 1 over sine, so same thing, sine theta cannot equal 0. So if you remember your graph of sine, which should look something like this, essentially it is at 0 at any multiple of pi. So therefore we can say theta cannot equal k times pi, where k is any integer. Now we'll prove this identity. So we have cotangent theta over cosecant theta equals cos theta. Now, I'm going to start with this side of the equation because it looks more complex and I want to simplify it. Cotangent, I can use 1 over tan, or I can use cos over sine. Now, because this deals with sine, I'm going to use a cos over sine. So cotangent theta becomes cos theta over sine theta. Meanwhile, cosecant is 1 over sine theta. Now, we have a fraction divided by a fraction. So that's the same as if I multiply by the reciprocal of this. So I've got cos theta over sine theta times sine theta over 1 equals cos theta. Our sines are going to cancel out, then cos over 1. So we have cos theta equals cos theta. So we have proven our identity. For our next one, we've got cos theta equals 1 plus cos theta over 1 plus secant theta. Now, we don't have any non-permissibles from this part up here, but we'll have some from down here. So secant, we know that our secant is 1 over cos. So therefore, cos theta cannot equal 0. However, what we also know is we can't have this equal -1 because 1 plus -1 would also give us 0 down here. So therefore, cos theta also cannot equal -1. Now we can figure out what angles we cannot equal by knowing our graphs of cosine. So if we just draw out a brief graph of cosine, this first one where cos theta cannot equal 0, we know that full cycle is 2 pi, half is pi. So therefore, our first zero is at pi over 2. So theta cannot equal pi over 2. And then that repeated every pi unit. So this was 3 pi over 2. So therefore plus pi times k, where k is any real integer. Now, cos cannot equal -1. That occurs at pi, and then it doesn't occur for another 2 pi. So therefore, beta cannot equal pi plus 2 pi k, where k is any integer. Okay, so now we'll go on to prove this. So I'm just going to rewrite it down here. So I've got cos of my angle is equal to 1 plus cosine over 1 plus secant. This side looks like the more complex side, so that's where I'll start. So I have cos theta equals 1 plus cos theta over 1 plus 1 over cos theta. So with this one, I'm going to do the same thing as I did with the last one to get rid of this extra fraction down here. So I'm going to multiply the numerator and denominator by cos theta. That gives us cos theta is equal to, now when I multiply the numerator, often I won't fully multiply it out at first. I will just leave it in factored form because sometimes things will end up canceling out. If things don't cancel out, then I'll multiply it out. So I've got cos times 1 is cos. Then I have cos times 1 over cos, so that'd just be 1. So we can see this term is the same as this one, so that cancels with that. So that leaves us with cos theta equals cos theta. And we can say identity proven. We'll also sometimes use our trigonometric identities to solve for a variable. So we'll be doing some solving like we were in section 9.2, except for we'll be adding in trig identities. So first example, use algebra to solve over the domain from 0 to 2 pi. We have 2 sine x equals 3 plus 2 cosecant x. So in order to be able to solve these, we need essentially everything to be one trig ratio type. So all sine, all cos, or all tan. So I will replace the cosecant with 1 over sine. So I've got 2 sine x equals 3 plus 2 times 1 over sine x. Now this still doesn't work well because we've got this fraction here. So what we can do is we can multiply both sides of our equation by sine x. So because we're multiplying one side by sine x, we have to multiply the other side by sine x. So that gives us 2 sine squared x is equal to 3 sine x plus 2. Now we can see that we essentially have a quadratic function, so we'll move everything to one side. So we've got 2 sine squared x minus 3 sine x minus 2 equals 0. We'll now product sum factor this. From product sum factoring, we get 2 sine of x plus 1 times sine x minus 2 equals 0. Now there's two different ways that our equation can equal 0. Either this function here equals 0, because 0 times anything is 0, or this part, if this equals 0, 0 times anything is 0. So at this point, I'll separate this into two separate functions. So I've got this one, so I'll have 2 sine of x plus 1 equals 0. And I have this one where I'll have sine of x minus 2 equals 0. We look at this one, first thing I would do is move a 1 to the other side. So we've got sine of x equal, 2 sine x equals -1. Divide both sides by 2. So that gives us sine x equals -1/2. We will then draw this out on a coordinate grid and find what angles this corresponds to. But first we'll deal with this one as well. So this one, same thing, we on our trig function on its own. So we've got sine x equals 2. Now, this is going to be no solution. Because if you remember from your graph of sine, if you don't have a number in front, sine is just going between +1 and -1. So it's never going to equal 2. So therefore, for this, we just have this one ratio that we're going to be using to solve things. So if we look at our cast rule, in this case, we've got sine is negative, sine is positive here and here, which means it's negative in these two quadrants. So I'll draw out two quadrant grids. One where we're in quadrant 3, one where we're in quadrant 4. Now sine, if you remember, is our opposite over our hypotenuse. So for these, our hypotenuse is 2, our opposite's -1. And you should recognize these as one of your special triangles. The other side of this being square root of 3. So it's our 30, 60, 90 triangle. However, we're dealing with our angle in radians. So this, which would be 30 degrees, is pi over 6 radians. Same as this is pi over 6 radians. So going from here to here, we know from here to here's pi, we're doing an additional pi over 6. So pi plus pi over 6 gives us 7 pi over 6. For this one, we're going all the way around to here. We're almost at the full 2 pi, but we're short by pi over 6. So we'd have 2 pi minus pi over 6. So that's going to give us 11 pi over 6. So our answers would be x is equal to 7 pi over 6 and 11 pi over 6. Okay, so our next one, we're solving over the exact same domain. And once again, we want to get to a single type of trig function. So we've got sine x equals cos x. What we can do is divide one of these over to the other side to create a trig function. Now, if we divide both sides by, say, sine, that would give us cos over sine, which is cotangent, which isn't the most ideal. We could use it still, though, but better would be dividing both sides by cos of x. Because sine x over cos of x is tan x. So we've got tan x is equal to 1. Now we'll quickly use our cast rule. Tan is positive here and here, where it's negative here and here. So we'll draw out two coordinate grids, one where we're here and one where we're here. Now, 1 is the same as 1 over 1, and tan is our opposite over adjacent. So that means that this side is 1, this side's also 1. This side's -1, this side's -1. So you should recognize that as one of your special triangles, and as such, you should know that this angle is pi over 4. Now, in quadrant 1, our angle is the same as our reference angle, so we know this one has an answer of pi over 4. This one, we need to go from here to here, so that would be pi plus pi over 4, which would be 5 pi over 4. So our answers would be pi over 4 and 5 pi over 4. Okay, practice work starts on page 653.